So in our last section, we started to, I think we had one question where we had to talk about catalysts. So let's go in a little more detail about catalysts, although it's going to be in other classes that you might take in the future where you might go into more depth with catalysts, such as biochemistry, organic chemistry, maybe if you go into some material sciences, a couple other classes like that. But we'll at least introduce the concept of catalysts and what we need to know for AP chemistry. So catalysts do increase reaction rates. How do they do that? They provide a new pathway for the reaction to proceed, and that new pathway lowers the activation energy required. So it's a little bit easier to overcome that. Maybe you're breaking different bonds. Maybe there's a way where the reaction. We'll talk about that as we proceed here. Catalysts are never consumed. So again, they are reactants in maybe a step one, and then maybe they're a product in step two. So they cancel out. They're not in the overall reaction, but they are they're still in these two elementary steps. So we can look at this graphically. And so we've talked about these graphs earlier. And so let's address the one we had previously. This is the blue. And if you look at the plateau, the beginning reactant plateau up to the top of the hump, that would be the activation energy or energy of activation. If you have a catalyst, all you're going to do is, in terms of this graph, is just lower the hump, the top of the hump there. So that's the difference between a catalyzed reaction and an uncatalyzed reaction in terms of that energy profile. There's either going to be no questions on the test or maybe one question on the test about the different types of catalysts. There are heterogeneous catalysts and there's going to be homogeneous catalysts. I think it's going to be a lot easier for us to find some information about heterogeneous catalysts, and those are going to be catalysts where the catalyst itself and the reactants aren't in the same phase of matter. So typical would be maybe a solid piece of platinum and maybe gases. That might be a typical heterogeneous catalyst. But here's a couple that I plucked out of the literature. One in the Haber process, there is solid iron. Another one we have platinum and rhodium. This would be the one that would be more real world for you, is catalytic converters. And I have a picture of a catalytic converter. Every car manufactured and driven in the United States has to have a catalytic converter. And that theoretically is to get all of the sort of quotations bad gases, poisonous gases, gases that aren't terrific for you and I or the environment, to react more than what they had previously reacted, to the point where that what's coming out of the exhaust is less noxious, less bad in quotations gases, less poisonous, so forth. So these gases, if you didn't have a catalytic converter, would be coming out of your exhaust pipe. But with catalysts, those gases are converted into gases that aren't nearly as bad to the environment, maybe like N2, maybe CO2. I know there's no way to find H2O in those, but those are the gases we would be happier emitting into the atmosphere as opposed to those. And the catalytic converter does that for you. Because the catalytic converter has those heavy metals in them, or transition metals, it's extremely expensive. It's one of the most expensive parts to your car. So here's a picture of a catalytic converter. Of course, every car is going to have a different catalytic converter. I pulled this kind of average. I know that's a tremendous range there, but it's going to cost somewhere in the $600 to $2,500 range just for the catalytic converter itself. And then, of course, there's labor involved, unless, of course, you guys want to try to put one on yourself. They're expensive enough that some people will actually steal catalytic converters. Certainly don't go trying to steal someone's catalytic converter, because obviously it's illegal. But you're going to have very, very, very bad gases entering the catalytic converter. This is prior to your exhaust. And then hopefully, again, the theory is then the gases that actually come out of your exhaust pipe. No, this is not your exhaust pipe here, but soon your exhaust pipe, not very far away from that, is that you're getting a little less noxious, a little less dangerous gases. There's a little more detail about that, but I think I had mentioned that you're going to have platinum, palladium, rhodium. They're expensive. Those are expensive catalysts. It has to happen in this grid kind of format because you want as many of these molecules of gas to pass through and come in contact with as many of these catalysts as possible so that the reaction takes place. I had mentioned there's a second type of catalyst, a homogeneous catalyst. Those would be same phase of matter. It was difficult for me to find an example of that, but here is a little example of that. If you take some, actually even AP Bio, you'll get into enzymes, and enzymes are a biological type of catalyst. And they, of course, every enzyme is going to be different, but they increase the rate of reaction tremendously. So reactions will take place very, very, very quickly. Enzymes are typically proteins, so they can be, if things don't go well in your body, the proteins could be denatured and the enzyme doesn't work correctly anymore. Also, there can be problems with some genetic defects where enzymes aren't being produced correctly, or they're just made just a little bit incorrectly. So what they're supposed to do doesn't actually happen. But they produce something called an active site. And this is that sort of idea of a transition state between the reactants and the final products. Living things have lots of different enzymes, and they're very, very, very unique. So the enzyme that converts this to this is different than the enzyme that does another job. Here would be a very, very simplistic look at what an enzyme might be. It doesn't really look like this in nature, but this gives you a little bit of an idea to kind of go with. So the enzyme has a very, very unique sort of lock and key mechanism, and it's only going to be able to come in contact and orient itself correctly with one particular substrate. And so that would be an example. Now, sometimes maybe your body is, the reaction's happening too much. So you might be able to take a medication, an inhibitor that might take up that enzyme active site so that the actual chemical can't get in there. And then the reaction's going to take place at a slower rate, maybe a safer rate. Maybe that inhibitor is not something that you're taking with a medication. Maybe it's happening for some reason in your body. So maybe it's a bad thing. A very complicated process of these enzymes, these substrates, enzymes, and inhibitors. Sometimes it's medication, sometimes it's not medication, but you can definitely, doctors, pharmacists can have an effect on these reactions. And again, a very, very brief introduction to catalysts. For us, I think the most important things we're going to need is understanding those graphs. You know, the less hump for the activation energy. If it's a catalyzed reaction, less activation energy, less hump. A greater degree of a hump if it's uncatalyzed. And then the other item would be if a catalyst, we'll use the word cat. So in maybe mechanism step 1, the catalyst is a reactant, and then maybe at step 2, it's a product. So yes, it cancels in the overall reaction, but you put it in and you get it out. And that would be a definition of a catalyst.